If we think back to what we learned about differential rate law, it's just regular rate law. So R equals K times A to some X and B to some Y value, right? That's basic rate law or differential rate law, okay? And so what differential or just regular rate law, I'm just going to call it regular rate law because it's just rate law. That's what you'll see, like when on the integrated problems, you guys can put your devices away, you don't need them. Okay, when we talked about integrated rate law, it said find the rate law, right? That's what that means, okay? So rate law is where we compare concentration versus initial rate. If concentration goes up, does our initial rate go up? If concentration goes down, does initial rate go down, right? Those are the things we're comparing. In our integrated rate law, we were comparing concentration over time, okay? So there's a different component. There's a different comparison that's happening in these two rate laws. This rate law has nothing to do with time. It just has to do with concentrations and how fast they're going to react based on those concentrations. Okay, so we're going to start out pretty simple. This says the rate of the reaction is 1.6 times 10 to the negative second molar per second when A sub O equals 0.35. There should be a molar after that. I just forgot to put in that unit. Okay, so what is this A sub O? What's that stand for? Original or initial concentration, right? That's its initial concentration. And that's its initial rate right here. Okay, and so rate just goes in to our equation as R. Okay, that's what R is. It's just the rate. Okay, and then here's our equation right up here. So do I have two reactants in my rate law? I just have one. So really my rate law for this one is going to look R equals K times A to some exponent, right? And what does the exponent tell us? It tells us the order of the reaction. So we still have zero order, first order, second order reactions, but we find them a little different way with these, okay? So we say we want to calculate the rate constant if the reaction is first order or if it's second order or zero order. So these are going to be three different rate constants, right? We're going to get three different answers here, okay? If the reaction is first order in A, then that means our rate law is R equals K times A to the what power? To the first, right? Just to the first power. And so that means when I go to plug in my values, I know my rate or my R value, 1.6 times 10 to the negative second. I'm solving, sorry, go ahead.
Because it's initial?
It tells us that it's first order.
Oh, okay.
So that's where my exponent comes from. So this is my rate equals K times my original concentration, right? Concentration of A is 0.35 molar, and it's to the first power. Okay? And then we just do the math there to solve for K. I don't need to do anything to that 0.35 because it's to the first power. So 1.6 times 10 to the negative second. You could put that into regular numbers if you don't like scientific notation. Divided by 0.35. And this is where we worked a little bit more to find the units for K, right? We did this originally, so give me the value of the K first.
0.046.
Good, that's what I had to, 0.046. And then let's look at units here. This is where we solved our units a little bit more carefully. Concentration here was molar. Rate unit is molar per second. Right? So really my molar is going to cancel. And so my units for K are 1 over seconds. Or you could list it as S negative 1 as well. Why do I have to put S negative 1?
Yeah.
Because that's, if you have anything to the negative 1 power, that just means 1 over that thing.
But I get that, but why do we have to put 1? Why can't I just put seconds?
Because the unit is not seconds, it's per second, right? The unit, if I'm trying to solve for K, I would have taken molar over seconds divided by molar, right? So my molars cancel and I'm left with just 1 over seconds. So that's how that works. Okay, so my units for K there are just 1 over seconds or per second, you could label it as. Are we comfortable with how we solved for k there? Okay, now we're going to find the rate constant if the order is second, if it's second order in k. So the rate law for a second order reaction would be R equals k times a to the what? To the second power. And so now I'm going to plug in my rate. My rate information is not changing, and my concentration information is not changing. My rate is 1.6 times 10 to the negative second equals k times 0.35 squared this time. Okay? My rate constant's not going to be the same for each of these because my rate is affecting it in a different way. I'm sorry, my concentration is affecting it in a different way. So I'm going to take 0.35 squared and take 0.016 divided by that. And the k value I got for a second order reaction is, I got 0.131 or 0.1306 or somewhere in that range. Okay? So let's look at the units now for that one. Concentration would be molar squared, right? Because 0.35 molar times 0.35 molar units would be molar squared. Agreed? And so my unit over here is still molar per second. And so what happens is a molar on the left cancels and one of the molar on the right cancels. And so when I divide over that molar, that leaves my units to be 1 over molar times seconds. Agreed? Right? When I divide that 0.35 over, that unit that I'm left with is really molar, and so that's going to be 1 over molar times seconds. Try to make that molar a capital M, like really make it a capital, not like this guy. Okay? I haven't remembered to do that as much, but that's my second order rate constant. And then if my reaction is 0 order, what does my rate law look like? It's just R equals K times A to the what? A to the 0 power. And what's anything to the 0 power?
1.
It's just 1. And so if this whole term is 1, do I even need to include it? No, the rate law for a 0 order reaction is just R equals K. And so we don't have to do any math with that, right? My K value here would just be 1.6 times 10 to the negative second. And the units just stay the same. So here it would just be molar per second.
Wait, can you explain how you do the math for, like, for the first order and the second order when you have 1 point, like, how did you get those?
For this, okay, so if I'm looking at this one right here,
Yeah.
0.35 to the first power is just 0.35,
Yes.
right? And so I want to get K by itself, so I need to divide by 0.35 on both sides.
Yes.
That's it.
Okay.
Yep. And then on the second order one, I had to square that 0.35 first, and then I divided it to the other side.
Okay.
Okay?
Thank you.
You're welcome. Okay, so this says sorry, mine's not cut up here. It gives us a table of data. And so here's how we know, let's talk about the difference between rate law and integrated rate law. Integrated rate law has to include time, right? It's time and one other concentration. This one gives us multiple concentrations and rates. So that has to tell us that we're solving for rate law. And it doesn't say find the integrated rate law. It says find the rate law. Okay? And so that tells us we're going to be looking at solving it in this way. Okay? So let's give the basic version of what our rate law would look like for this particular problem. It would be R, can you see that green okay? R equals K times our first reactant, which is it's an I. So iodine monochloride. Okay, so this would be ICl to some X order, and then it would be H2 to some Y order, right? That's not our final rate law. What's going to give us our final rate law? Like, what has to change in order for our rate law to be final? We have to put in a number for the X and the Y, right? We can't just leave our rate law with an X and a Y. We've got to know the order to give us a final product of our rate law, okay? So to determine the order, remember, if we look at this, we're going to let's look at ICl first. So this means I'm solving for X. right? Because I'm solving for my exponent up here. I want to look at where is there a change in ICL, but not a change in H2. Which reactions do we see a change in ICL, but not a change in H2? Reactions 1 and 3. Okay, because if I want to focus in on how the concentration of ICL affects the rate, I want to make sure that H2 is held constant for those two reactions, right? I want to only focus on ICL. So I'm going to say in reaction 1, my concentration is 0.1. The rate is 1.6 times 10 to the negative 3. In reaction 3, my concentration is 0.2, and it's 6.4 times 10 to the negative 3. You don't have to rewrite these. I just like to focus in a little bit more. And then I'm going to look at what is the ratio of these increases or decreases. So my rate, I'm sorry, let's talk about concentration. My concentration increased by how much? From 0.1 to 0.2, it increased by a factor of 2, right? It doubled. My rate, did it increase, decrease, or stay the same? It increased, right? If you need to write it out differently, it's 0.0016, 0.0064, right? If that helps you to write it out that way, you might be able to see it a little bit clearer. My rate increased by what factor? By a factor of 4. If you're not sure, take the bigger divided by the smaller. So 0.0064 divided by 0.0016. So if concentration increased by 2, 2 to what power equals my rate increase, right? 2 to what power equals 4? Okay, is this coming back to us a little bit? Okay, good. So my X order, or the order of my reaction for ICL, is going to be a 2, right? It's a second order with respect to ICL. Okay, now let's look at H2. Sorry, do we have any questions with that one so far?
So this is taking us back to how...
Right. This is rate law, not integrated rate law. Okay? So if I look now at solving with H2, that means I'm really solving for like Y. Okay, because Y is the order exponent there. So I want to look at two reactions that change for H2 but don't change for ICL. So it really looks like I should be looking at reactions 1 and 2, right? Okay, my concentration goes from 0.1 to 0.2. My reaction goes from 1.6 to 3.2. And so that means my concentration increased by a factor of 2. My rate also increased by a factor of 2, right? They both just doubled. And so that means 2 to the Y power equals 2. So that means Y needs to equal.
So for Y, we don't have 2. Okay, can you explain how you chose what you did?
Why did I choose these two reactions?
Yeah.
Yep. Okay, so if I want to study the reaction, if I want to study the effect of H2, if I want to find the order for H2, which is what I want to do right now, right? I'm trying to find that exponent. If I want to find the order for H2, I need to find two reactions in which their concentration changes. So H2's concentration is changing, but the other reactant need to stay constant.
Oh, it just flips. Okay.
Right, they want to stay constant. Because if I'm trying to study H2, I can't have ICL changing too, because then I don't really know where are my changes coming from. Are they coming from H2 or are they coming from ICL?
Okay. Will we ever have to like we're given this?
When we solve for integrated rate law, they ask us to find the regular rate law too, but that's just for reactions with one reactant, right? We only do things with integrated rate law with one reactant. We don't do it with multiple. Okay, so my finalized rate law would be R equals K times ICL to the second order times H2 to the first order. Okay, do you remember what it means when it says overall order? You know how to do that? Right, you just add your exponents. That's it. Overall order, we're going to take second order plus first order, so 2 plus 1 equals 3. That's literally it, right? Okay, last part here, it says, if my initial concentration of ICL is 0.3 and my initial concentration of H2 is 0.2. What is my initial rate? So up here we studied the rate based on this set of concentrations. It's almost like we're just adding another trial and saying this one is 0.3, this one is 0.2, and we're just trying to solve for that guy right there, right? But we can do that because we know the rate law. Okay? So if I'm trying to find the rate, that means I'm solving for R. I need to know what in order to do that? I need to know K first. So if I tried it just like this, 0.3 squared, 0.2 to the first, right? The problem is I've got two variables there that I'm missing. So how can I solve for K first in order to be able to go back and solve for R? Do you remember that?
Pick one of the initial rates from the table.
Bingo, right? I'm going to pick one of the sets of data that's already provided, and I'm going to solve for my K value, right? I'm just going to pick one of the sets. So, I don't know, probably number 1, right? I'm going to take a look at just this first trial and say my rate in this trial was 1.6 times 10 to the negative 3 equals K times 0.1 squared times 0.1 to the first. And I'm going to solve for K. Okay, I got my K value at 1.6. Let's see if we can get the units for that. Once you've got that value, let's see if we can find the units for that. Anybody having trouble getting that to come out?
Did you say you got 0.16 or 1.6?
I got 1.6.
Oh.
Did you square that 0.1?
Can you show how you wrote that?
Okay. Sure. Units there, after we've got all of them plugged in, I end up with 1 over molar squared times seconds for my units. So that's still not really answering my full question, right? My full question said calculate the initial rate if you have these concentrations. So knowing our K value, let me give myself some room up here. Now I'm going to solve for rate equals K times 0.30, that's to the second order, 0.20 to the first order. Okay, so this rate I got to be 0.0288 molar per second. I want you to see, does that answer seem reasonable based on your data provided in the chart? Right? Based on all of this data, as our this is 0.0016, 0.0032, 0.0064, right? As our concentrations got ramped up a lot, now we're at 0.0288, right? We see an increase in concentration, we see an increase in rate, so I think that seems reasonable, right? You don't have to see, like, does it match up exactly, but if we would have gotten a final concentration of like 0.000024, right, that really wouldn't have made sense. So just make sure to check yourself, like, is it reasonable? It wouldn't have made sense for our concentrations to keep increasing and our rate all of a sudden to go down, right? That wouldn't have really made sense. So just make sure you kind of check to see, does your answer seem reasonable? And in this case, I think it does. This one asks for the rate law, rate constant, and the initial rate for trial 6. If we want to find the rate law, let's write out just the basic rate law for the reaction first. It would be R equals what? K times A to the X for right now, and then B to the Y. Let me remind you here that the coefficients in that problem does not affect our rate law, right? The coefficients don't make a difference with our rate law, so don't worry about that stuff. As you get a little bit more in advanced kinetics, they will start to make somewhat of a difference, but for right now they really don't. So if I'm trying to look at A's exponent first, or X, I need to pick out two reactions in which A has changed but B has not. So first of all, we need to look to find two reactions for B that are the same.
2 and 4.
Right, I only really see this one and this one. And so is there a change in A between 2 and 4? Yeah, so we're good. Okay, so in reaction 2, my concentration's 0.240, and it goes to 0.120. And so I say it decreases by a factor of 2. You could also say it's decreased by a half. That's fine if you want to too, right? I just don't like fractions, so I'm just thinking about it decreasing by a factor of 2. You could say it gets cut in half. It doesn't matter with that. Okay, my rate goes from 2.0 down to 0.50. And so that decreases by a factor of what? 4. And so that means 2 to the x power equals 4. So x has to equal 2. Right? My exponent or my order for my reactant A has to be 2. All right. As I'm looking now for the order of B, I'm trying to solve really for Y up here. I've got to find two reactions in which B changes, but A stays the same. So what can we look at there? Yeah, you can look at 1 and 2 if you want. Okay, reaction 1 goes from a concentration of 0.480, I'm sorry. And my rate is 8 to down to 0.120. My rate is 2. Decreases by a factor of 4 and decreases by a factor of 4. Which means this is 4 to the y power equals 4, which means y is equal to 1. Right? This is just coincidental that it's the same rate law as the last one. I didn't really mean to do that. Okay, so my final rate law, we don't have to put in new compounds, it's just A and B here. So it would be R equals K times A squared B to the first. Remember, if it is a real reaction, we do put in the real compounds there. Right? Yeah. So there's my rate law. Since our reaction is just A and B, we just have to keep A and B in our reaction. If it was C2H4 plus O2, we'd put those in as our parentheses. Okay, calculate the rate constant. How do I do that? I pick one set of data. Doesn't matter which set you choose. I'm just going to choose number 1 to solve and find K. So my initial rate is A, K times 0.240 squared, 0.480 to the first. And I'm going to solve for K there. I'm going to get rid of this data over here. I got about 289.4 for my K value, okay, or somewhere in that range. Okay, and then what would our units be here? We've already seen one that had units similar to this, right? Molar squared, molar, and this is molar per hour. We got to pay attention to that with our rate here. Molar per hour, so the molar, single molar will cancel, and that means our units would be like 1 over molar squared times hours.
Is concentration always molar?
Yeah, or sometimes they'll list it as moles per liter, which is the same as molar. But it should be listed, I forgot it up here in the table, it should be listed here beside it.
And if it's not, just assume it's
Yeah, if it's not, just assume. Or you can look at what the rate is there. That would be your concentration here, too.
So
Yeah.
basically, anytime you have like exponents, like if there was another problem that had those same exponents, you should have the same.
The units would be the same.
Okay.
Right. Right. And if it's a single order, that's, if they're both first order, then it would be like 1 over molar times hour, right? Yeah. Okay, calculate the initial rate for trial 6. So all that means is that we're just trying to solve for that guy. And so we've already got K. So my rate equals 289.4 times 0.014 squared, 1.35 to the first. These concentrations that are given are kind of all over the place, so it's going to be hard to find a predictable number here. We'll see what we get. And then units here go with whatever was in the table for rate. So molar per hour. So I think there it's difficult to see, is our answer reasonable or not, right? The thing you see is that this second order reactant took a big hit. And second order means that its concentration affects the rate more so than a first order, right? That's what that means. If it's second order, its concentration has a heavier, the rate is more dependent on that than B. And so we see a huge concentration hit for component A and a pretty big concentration fluctuation for B. So that one's a little bit harder to see, is our answer reasonable or not, but I think it does. I think it does fit because we see a steady decrease pretty much in concentration as concentration goes, in rate as concentration goes down. Here we see a pretty low rate and our concentrations are both pretty low. I wouldn't stress too much about is it reasonable, but as long as we don't get a rate of 7,000 or 700 or something crazy that's off our charts, I think we'll be okay. All right, rate constant here. I got 230. If I work the math with that, is that what you guys had? 230, and then units would be 1 over molar squared times what? Seconds, right? Because rate was molar per second. So 1 over molar squared times seconds. Overall order, we just add up our exponents, which is a total of 3. And then the initial rate for an experiment, so we've got our K already, so we can just go ahead and go R equals K times 0.150 squared times 0.200 to the first. And so when I worked that, I got 1.035 molar per second.